Hello, fellow problem solvers. So today we're going to be doing a problem from the IMO 2010, problem number 3. This is a phenomenal number theory problem. I suggest you try it out for a minimum of an hour, ideally 2.5 to 3 hours, not more than 4.5. On the other hand, if you'd like to go along with us, give it at least the next 20 minutes just to understand what's happening here. It's a simple function, and I love this problem. It really teaches you how to think in one way with functional equations. I just find this very cool as a problem. So now let's begin. We're tackling a number 3 problem. Oh my God, so scary. How are we going to ever do that? And the point of this video and videos that tackle hard problems is to sort of dispel the myth that these are like some amazingly difficult ideas about the distribution of squares and their prime factors and whatnot. No. Take it step by step by step by step. So what do we have here? This is symmetric in m and n, so plugging in m equals n makes 0 sense. Now this is a perfect square for all m and n. Okay, so a solution is g of m is m, and that gives us m plus n squared on both sides. Is that the only solution? I don't know, right? It's not entirely clear. Could we have another solution? Maybe let's deal with that later. Right, we can deal with that later. And let's try to see then, okay, what do we have? Well, saying this is a solution, it's probably then an injective function, right? Let's see what happens if it's not injective. If, say, g of a is equal to g of b is equal to some c where a isn't equal to b. Okay, then it would make sense to plug in. Well, if we plugged in, we have c plus a times c plus b is a square, so I don't know, maybe this is something cool, maybe it's not. Now let's see what happens when we plug in c and x. So I'll call this, the fact that this is a, a square, I'll call this p of mn, implies this is a square. So instead of me saying plug in a and plug in x, I'll just write p of ax gives us c plus x times g of x plus a is a square, and also c plus x if I plug in b and x, and g of x plus b is also a square. And I can pick whatever x I like. So what does this tell you, right? What kind of x should I want to pick? Okay, pause for 5-10 minutes and see like what x would you pick here. And for me personally, I would just try, well, let me pick a square, because if this is a square, if c plus x is a square, let me make c plus x a square, then this will have to be a square. Maybe there's an argument there to be found. And I have, if I pick x to equal some y squared minus c, for any y, I'll have that g of y squared minus c plus a and g of y squared minus c plus b are both squares. Okay? Now the thing is, these are two squares, but this is the same thing, right? G of y minus c plus a and plus b. And we have two squares that differ by a minus b, right? Whichever one is bigger. When you say that a is bigger than b, they differ by a minus b. They also differ by b minus a, it doesn't matter, but they differ by a minus b. So that means as y grows, there's only a select number of squares these things can be equal to. There are infinitely many numbers of this form, but they can't be too large, because otherwise we'd have squares which differ by a lot. As an example, they can't be, say, this can't be 1000a squared, right? This can't be equal to 1000a squared if a is bigger than b, because if this was 1000a squared, then we'd have this is equal to 1000a squared minus a plus b. And then this thing, 1000a squared, right? This is just like it's not reaching to the squares which are around it are 1000a minus 1 squared and 1000a plus 1 squared. But this can't reach that. So they're limited in size. And that means we'll have infinitely many numbers which are going to be, in a specific range. So we'll have actually one number will come up for infinitely many times, and then maybe there's an argument to be made there to finish up, right? Pause for 5 minutes, think about this. And for me, the thing is, yeah, it can. I'm just proving injectivity with this. Like, will I be able to push this forward in some way, shape, or form? I don't quite see it yet. So let me just try another thing. Like, why am I too bogged down in this making this a square? Right, I can explore this idea a bit and see I'll probably be able to get to some sort of contradiction with this. Right, I'll have to deal with something that it feels messy to me. Maybe you've tried it out and you saw something not messy. Please let me know in the comments below. Like, learning what you think, how you solve a problem, lets me learn how I can better solve problems. So the other thing is, okay, instead of making this a square, what else can I make it to force it? To force this to be of a certain type. And right here, pause for 2 to 3 minutes, think about it. What else, aside from making a square, forces this to have some characteristic? Well, if I make this equal to a prime, this is equal to p, if I put x is equal to some prime minus c, what does that mean? Well, this is divisible by p, so this thing must be p times some s squared, right? This must be, so g of x is equal to p times some s squared, a plus g of x is that, and b plus g of x is equal to p times some t squared. You don't necessarily have to be the same thing, but both of these are now divisible by p. What does that give me? And the answer is, pause for 2 minutes if you figure that out, please. When I subtract, it means that p divides a minus b. Now this is an arbitrary prime, right? So I can make this equal to an arbitrary prime, arbitrarily large. I can pick a prime that's bigger than a minus b, and then that forces a contradiction, because this is smaller than p in its absolute value, and because a is greater than b, this is 1. So this forces a minus b to be equal to 0. In other words, the function is injective. Now with that, I invite you to pause for 20 minutes. See, is there anything else now you would do with this problem? Like, what would you do next? Pause for 20 minutes, think about it, push some idea. Let me clear this up. And now, okay, now I have cleared this up. I have the function g is injective. Okay. I'm really thinking about, maybe let's look at, prime factors of these. So say I have, if the function is, say, g of n, like maybe I want to put one of these to be equal to a prime and then get the other to equal to a prime. Maybe one thing to try to do is to see when do these things share. Like, does p divide g of p? Always. And also, what if f of 1 is equal to 2? This is also, if you don't have an idea, just plug something in, see what happens. Let's see, like, does this force our function in any way, right? G of x isn't equal to x in this case. Actually, g of 1 is equal to 2. So we plug in a 1. If p of 1 and x will force that g of x plus 1 and x plus 2 is always a square. Okay, so now if I plug in a 2, then so g of 2 plus 1 is a square. I have g of 3 plus 1, so if I plug in a 3, is going to be equal to 5 times some square q squared, right? g of 4 is g of 4 plus 1, because this is 6, this is going to be equal to like 6 some t squared. Now, can this actually, could you set up g of 2 for this to be a square, this to be a square, this to be a square? Like this to be 6 t squared, 5 q squared, and some like a squared. And the answer for me is like, wait a second, I can. Right? Like in general, I need g of n plus, what's it called, 1 to be equal to n plus 2 times some square. Like realistically, this is what it is. And maybe divided by some, maybe I can get out the factors of n plus 2, which are squares. Right, yeah, I can definitely do that. But I can just set g of n to be equal to n plus 1. And then I'm done. Then I can do that. So it seems g of x is not the only solution, but also we can have g of x is x plus some constant c. So now this changes the game just a little bit. Because now, okay, now we can't figure anything out about plugging it, like if f of 1 is equal to something we don't know anything about. Like we can't, there's no contradiction to be had. Now there is a contradiction. If say f of 1, g of 1, I mean there's maybe a contradiction if g of 1 is equal to 2, and then if g of 2, I need this to be some square. So let me put g of 2 is equal to, instead of 3, let me put this is equal to 8. And now let's see like what is the contradiction, right? That is sort of the way that you can, if you don't have an idea for what to do, and this can happen in difficult problems like this, you're like, what do I do? You can look at actually plugging in specific stuff if you have some background technique, background knowledge, and have solved a lot of problems. That exposure gives you ideas. Or you can say, okay, what happens when I do this? So if I have now I have g of x plus 1, and x plus 2 is a square, times x plus 2 is a square, and g of x plus 2 times x plus 8 is a square. Okay. G of x plus 1, g of x plus 2, these are squares. X plus 2, x plus 8. What do we want to do with x? What kind of x do we want to set up? Pause for 5 minutes, think about it. How would you get to a contradiction here? And for me, and the thing is, wait, let me see if I can do that divisibility thing again. I don't have to make this equal to a prime. I can make it just divisible by a p, but not p squared, for both of them. And this prime will either have to be 2, I know there are some catch cases there, or a 3. So let me just try to make both of them divisible by 3. So let's put like x plus 2 is equal to like some 3 times some big A squared. X plus 8 is then going to be 3 times some A squared plus 6, right? Which is 3 times A squared plus 2. Maybe there's a contradiction to be had that this is A squared plus 2. Who knows? So, yeah, let's see what will happen. So now this forces that g of x. So for this x, we're going to have g of, let's do this, 3a squared minus 2, because that's what we're plugging in. This plus 1 is going to be equal to 3 times some b squared, and g of 3a squared minus 2 plus 2 is going to equal 3 times some c, actually 3 times something. But this obviously can't be the case because these two can't both be divisible by 3. They're relatively prime. And that's a contradiction. So this is how we're getting a contradiction if 2 isn't 3 and g of 1 is 2. So now with this idea, Try to develop your own. Develop your thinking. Try something out. Can you generalize this? You can even say, let g of 1 be equal to c plus 1. Or just let it be equal to, I don't know, c plus 1 or c, whichever one you fancy more. And then say g of 2 isn't equal to, let's actually try to do that. If you don't have any, and you're just trying something out, like try the very basics, like g of 1 is going to equal to c, g of 2 isn't equal to c plus 1. Why is there a contradiction? Fine, try it out right now and see what you get. Let me clear up the board and get back right what we've found so far. So far what we've had is, we really don't have much. We have g, we have this, and we have that g is injective, right? That's all we have. So what happens if g of 2 isn't c plus 1? Let's see what happens. So first let's do the thing where let this be equal to, let g of 2 be equal to some d. Just so it's like easier to write. That's why I'm writing these variables, because it's easier sometimes to see, at least for me, if I have c and d, like what is it that I'm working with. So if I plug in 1 and x, and I'm gonna plug in 2 and x, and let's see what I get. So I get c plus x times g of x plus 1, and I'll have d plus x times some g of x plus 2, right? This is pretty much what I have. Now, the thing is, what happens if, what did I do before? I made these equal to a prime that divides both of them. Now, there's going to be an issue if if this is c minus 1. I see, like there's going to be an issue with that. Oh, but let me just like make one more thing clear. C plus like p of 1, 2, like gives us some sort of something about the relationship between c and d. It tells us that c plus 2 times d plus 1 is also a square. Maybe there's something there, maybe there's not. But let's see. Let's assume also d isn't equal to c minus 1, and let's get to a contradiction with that. You know, it's not equal to d plus c plus or minus 1. Okay? Now, what are we going to see? They're going to say, well, in this case, we're going to get d minus c is going to be divisible by some prime. So let's say it's divisible by this prime p. And then we set x to be x plus c to be equal to p times some square. And then we get the prime divides. Actually, let's see what we get. Let's set then x plus d is going to equal, well, px squared minus c plus d. Now, this is divisible by p, this is divisible by p. So let's actually make d minus c be equal to p times some a. Just see what it is we actually have. Then here we have, this is p times x squared plus a. Okay? Now we have p divides g of x plus 1, but do we have p divides g of x plus 2? Pause for 5 minutes, think about it. The answer is not necessarily. I mean, not for all. We need to think about what kind of x we're going to put in. But the trouble is that, first of all, say this prime is, say this is a power, say d minus c is a power of 2, like 2 to the alpha. Then x, then c, say c and d are powers of 2, 16 and 8, right? Then this thing could be divisible by p squared. Like we could have a p dividing this. And if this whole expression is divisible by p to an even power, p squared, then we don't have a guarantee that this needs to be divisible by p, so we don't get our contradiction. So now we need to think more deeply, like how are we going to avoid this contradiction? With that, yeah, I'm sure there's maybe some edge cases. It's important to look at this. Maybe for 2 and 1, there might be an edge case that just breaks this solution apart. But what do we do here? Because this is what we're like. This is the trouble we're having now. We don't know the shape of this immediately. Let's sort of try that out, see what happens. This is what you do when you pause and you're confused, like, I don't know what I really have. Plug in specific values, see what you get. Let's forget about this thing for now. And the reason I want to forget about this thing is because it gives me some constraints, but I personally don't think it gives me that much constraints here. I think like in general, like I can have primes can take up a weird shape. Like c plus 2 can be some huge prime squared, and this could be some huge other prime squared. Or it could be like that prime to the power of 4. I mean, potentially. And I don't think it's really constraining me that much. And that d minus c could be, again, a power of 2. It's not giving me a super big constraint, and it's just one equation. Versus this is with x, and x I can manipulate to be a lot of different things. So now, let's see like this very specific case. D is equal to like some 2 to the alpha plus 1. C is equal to 2 to the alpha, right? And then we're going to have x plus c is going to be equal to 2 times some x squared, or x plus 2 to the alpha, and x plus 2 to the alpha plus 1 is going to be 2 times, is going to be forced to be 2 times x squared, and then it's going to be minus 2 to the alpha plus 2 to the alpha plus 1, which is going to be equal to x squared plus 2 to the alpha. Now, if this is 2 times x squared times 2 to the alpha minus 1, now sure, I can pick an odd x, and then I'm cool. Actually, if I just pick an odd x, it seems like I'm in the clear. Now, what kind of x do I have to pick in general? If this is not some 2 to the alpha, if this is divisible by some prime to make this not divisible by prime, do I always have that? For, for any, if this is p times some a can be 1, negative, well, like anything, do I always have that? Such that this isn't divisible by a prime, and it seems to me, on the first glance, and I just suggest on the first glance, like I do. Like here, I would pick an odd x, here I would pick an odd, this would still be true, and I'd have divisibility by 2. Now, with this in mind, I want you to pause for 10 to 15 minutes and try to push this problem further, even think about maybe beyond 1 and 2. Put it all together and see what is it that you notice. Try to wrestle with the problem a bit. And now let's clear up the board. Okay, so let's finish our idea with g of 1 is equal to c, g of 2 is equal to d, which isn't equal to c plus or minus 1. And now what do we have? We have that, so we're gonna have set, so we had g of x plus 2 times, x plus d, and g of x plus 1 times x plus c. Let c minus b, d be equal to p times some a. And now let's set x plus d to be, let's make c is greater than let's not actually deal with that. Doesn't matter which one's greater or not. A can be positive or negative. I don't think this changes divisibility. It changes the sign, but not the divisibility. This is p times sum capital X squared, which means x is px squared minus d, and then x plus c is equal to bx squared plus c minus d, which is equal to p x squared plus pa, which is going to be p times x squared plus a. Now, also what's important to note here, if x is divisible by p, from here we still have that p divides g of x plus 2. Because it's an odd prime power that divides x plus d, so there must be, we're missing really a p here. And for this one, so can we always plug in an a? Can we always plug in an x? Well, now I think it's like quite actually simple, because if a is divisible by p, we can plug in x is congruent to 1 modulo p, and then this isn't divisible by p, neither is this, so this is all divisible by just 1p. And if a is also, say, divisible by p, like this could be p squared, p cubed, p to the 4, then we can just plug in that case, we can plug in, what's it called? In that case, we can plug in a 1 here. In that case, we plug in 1 modulo p. If a isn't divisible by p, we can just plug in x is p times something. And then the whole thing isn't going to be divisible by p. So in both cases, we will get that p divides this and p divides this. A contradiction, because then p divides 1. Now, with that, we have something for 1 and 2, right? We've shown that g of 2 is either going to be c plus 1 or c minus 1. Now, the trouble is, what happens if g of 2 is c minus 1, right? If g of 2 is now c minus 1, g of 1 is c, what does that equation become that we had before? It becomes 1 plus g of 2, which is c, and then 2 plus g of 1, c times c plus 2 is a square. And this is this ever the case? It's my question now. Is this ever the case or not? Because this is c squared plus 2c, and this is less than or equal. Is this strictly less than c squared, and strictly greater than c squared, and strictly less than c plus 1 squared, so it's not a square. Okay, now this part is not generalizable at all for when we get other numbers here. But is there something about g of 1 and g of 2, about this whole process that we did, that is potentially generalizable to other numbers? Are we ready to tackle our whole problem and not just worrying about what g of 1 and g of 2 is? Because now we've shown that g of 1 is c, g of 2 is c plus 2. Is there something with that we can use to now look at n? Because now we have g of x plus 2 and x plus c plus 1, and g of x plus 1 and g of x plus c. Both of these are squares. Maybe there's something now that we can figure out about, specific, what happens if we plug in x is equal to 3. Does this give us anything for me, or does it give us something for specific x? Perhaps if x is p minus some c, then g of x plus 1 is divisible by that prime. Can we make it so that it's equal to that prime minus something? I don't know. Right? Is there something we can do with that? I don't know. I don't know. If it's not, maybe there's something here that we get, right? I mean, let's check that out and see if it's too difficult or not. So if we plug in x plus c is equal to some prime p, then we're going to have g of p minus c plus 1 is going to be that prime times some a squared. I'm not using the same a I had before. and then g of p minus c plus 2 is p times a squared plus 1. Now, what is this now? G of, this is going to be, p plus 1. So p plus 1, if it has some odd factors, this thing has the same odd factors. What do we get anything? I don't get anything right now. From here, from this, I just don't see anything. That's me personally. Maybe you do. But I want to also go down back to what is it we use for for 2 and for 1, right? If you can pause here and try to solve the problem, it's going to be a very good exercise. But now what we can see is, well, let's look at, instead of g of 1 and g of 2, let's look at any two consecutive numbers. Because we looked at the fact that these two are relatively prime. And what we had, on the other hand, is if you have, say, g of n plus x, let's make g of n be equal to some c, and g of n plus 1 be equal to d, which isn't equal to c plus or minus 1, right? Then what we have is x plus c times g of x plus n, and we had x plus d times g of x plus g of x plus n plus 1. Now if c minus d is divisible by is equal to p times a, we can literally plug in the same thing we did before. Because nowhere, mind you, nowhere in this do we use the fact that we were working with 2 and 1. That this was like, we did not use the fact, we used the fact that these were c and d. Not the fact that these were 2, we only use 2 and 1 in the fact that these are of a difference 1 between each other, right? That they're consecutive. That's the only way we use this thing. And that is an important thing to notice in your problems when you're solving something and you're playing around with these base cases or smaller numbers, and you're exploring the problem, is to notice, wait a second, what exactly did I use about them? Did I use the fact that 1 and 2 are small? No. I used the fact that they're consecutive. And when you notice what fact you used, what fact you didn't use, then you can see what you can generalize. And when you can see what you can generalize, that can get you to it closer to a solution. And now what do we have? These two numbers are always squares. And now we'll get literally if these two numbers, if c minus d is equal to p times a for some prime p, then we're going to have by plugging in this, we can plug in an x that's either divisible by p. If a isn't divisible by p, actually, wait a second. If a is divisible by p, I can still plug in an x that's divisible by p, right? Because then this will just, I don't know the power of a, so I won't do that. If a is divisible by p, I'll plug in x is congruent to 1 modulo p, then this will be congruent to 1 modulo p, and then all this will be divisible by only p, not p squared, and this will be only divisible by p, not p squared. And so it will follow, but on the other hand, if a is not divisible by p, I plug in x that's divisible by p and I'm done. Just like that. And so we've, with that, shown that these two numbers, x plus c and x plus d, so their difference, c minus d, cannot have a prime factor. Which means what? Their difference is, and they're not equal, so it's not a 0, but their difference is then plus or minus 1. So in other words, we have g of n plus 1 minus g of n, like their absolute value is equal to 1. That's the same thing as me saying their difference is plus or minus 1. Now with this idea, okay, so what is our function like? Well, it starts off at c, it goes to c plus 1. And now, under what condition will we not have our solution g of x is x plus c? Pause for 3 minutes and think about that. And the answer is, for what c? Well, if we have a we know at first it goes up. Yeah, like that's actually what we proved with G of 1 and G of 2. By sheer accident, I would say. But I didn't expect to prove this, really. And now we have G of 3. Well, it's either going to be G of 2 plus 1 or G of 2 minus 1. Well, it can't be minus 1 because then we have by injectivity. The thing we proved previously, which I forgot to write down, is we have a contradiction by injectivity. So G of 3 must be that. G of 4 must be up. And we can say by induction. We're assuming that G of n is equal to n plus c minus 1. For n is, we know this to be the case for n is equal to 1 and 2. Assume it's the case till some k. Actually, assume it's the case that G of k is equal to k plus c minus 1, and G of k minus 1 is equal to k minus 1 plus c minus 1. And then for G of k plus 2, we have by this thing right here, actually for G of k plus 1, we have for this thing right here, that's equal to G of k plus or minus 1. In other words, it's either equal to k plus c or k plus c minus 2. But if it were equal to k plus c minus 2, it will be equal to G of k minus 1. Given these two are equal, it's not given these two are different, it's not equal to this, so it's equal to k plus c, and then by induction we have our problem. Now, I personally did not figure out that actually when we plug in G of 1 is c and G of 2 is c minus 1, we'll get a contradiction. I didn't figure that out when I was solving this problem. For me, the idea was I figured this out, and then I used the injection part saying that if from f of 1 we went down, we can't ever go up. But if we can't ever go up, if we start at c and we're at c minus 1, we're going to reach 0 after c steps. Then G of c is going to have to be 0, but that's not in our domain, and actually it's in the codomain, and so it's a contradiction. Right? That's the way I've proved this fact. But through this video and like thinking about what I'll say to you, I've seen that I don't need that fact. If this is correct, I think this is correct, right? Because it's c minus, if it's c and c minus 1, then I get this. Quite nice, I must say. Well done you. And this finishes up our problem. And I thought this was a very, very cool problem because it's a step-by-step. It sounds scary at the beginning. Oh my God, I'm dealing with a number 3, but we didn't talk about the distribution of squares and the prime factors and primes, nothing. Just a simple bada bing, bada boom, bada bam, and done. This finishes up our problem, and as always, thanks for problem solving.